Come on in, everyone.
Good morning, Mr. Younger.
Good morning. Ask me any questions if you have any while we're waiting for everybody else to come in. Trying to get my notebook in order here so I can take notes. All right, now I'm ready to roll. Darren's having a hard time getting in. I don't know why. Might be something on his side. All right. So sorry about again today, folks. I was hoping I'd be able to come back today, but I was sick. I almost canceled classes altogether because I'm sick. I'm running a fever. I feel horrible. But anyways, pretty confident I'll be back Wednesday. I'll let y'all know by 5 p.m. on Tuesday if that's not the case. So just assume we're going to meet at lab at 9 a.m. on Wednesday, unless you hear otherwise from me by 5 p.m. on Tuesday. So, anybody have any questions on any material so far, homeworks or anything like that? Is my video quality look okay from y'all side? Because it's saying my
I
connection
do
is
have a
stable.
question.
Go ahead, Shonda.
I can see. Yeah, just the introduction to mastering physics. That's just for practice. It says it's not for scoring.
Yeah, I
It's
think I put the
homework that was
practice
due
one
today.
where it's not worth any points on there for that. So yeah,
So it's not a time to limit to get it in. It's just practice.
right. Yeah.
Yeah.
And if
Okay.
you
Because
had it
I did
last
the
semester, you probably don't need it anyway. So
yeah, well the physics primer was scored, I think, but the introduction to mastering physics was practice.
I count them in my extra credit anyway. So even the ones that are scored, I still count it as like I say I'm going to drop two of the lowest, but I really drop four of the lowest if I do physics primer and intro.
Okay. I just wanted to double check because it says due tonight. So
Yeah, if you've had a semester with us, you wouldn't need it. I would say any of these students that maybe hadn't had mastering physics last semester or when they took 241, they might want to do it. Other than that, don't worry about it. Anybody else have anything? All right. Well, we last time were into and completed chapter 18. Now we move on to chapter 19. And chapter 19 is basically where we start to learn about thermodynamics. We're going to learn first off the first law of thermodynamics, which is basically just a statement of conservation of energy. And we're going to learn about specific heat and what we call calorimetry experiments. So if you ever did the specific heat lab last semester, then you have some sense of what it is. But specifically, specific heat is the amount of energy required to change the temperature of a substance by a certain amount. For instance, the calorie is the unit that we use, lowercase c-a-l. That's the energy required to raise 1 gram of water from 14.5 to 15.5 degrees Celsius. They had to be very specific because the specific heat actually changes for a given temperature. But to be honest with you, your book points out that from 0 to 100 degrees, that specific heat doesn't change by any more than 1%. So you can pretty much use 1 calorie per gram per Celsius degree or 1 kilocalorie per kilogram per Celsius degree for the specific heat of water. All the way up to 100 degrees Celsius, and you won't be off by more than basically 1%. So, any questions on that kind of stuff? Any questions on past homeworks? I'm always going to try to remember to offer you a chance to have homework questions answered, but I will occasionally forget. So make sure you ask me if I ever skip that part and you actually have a question. It will not bother me. All right. So let's get started. I'm going to tell you initially about your book. Your book calls Jewell, James Prescott Jewell. I think that was his first name. Let me double check on that one. Yeah, we're in chapter 19. Chapter 19 is called Heat and the First Law of Thermodynamics. And the sections of that are heat as energy transfer. Section 19.2 is internal energy. Section 19.3 is specific heat. 19.4 is calorimetry, solving problems. 19.5 is latent heat. And 19.6 is the first law of thermodynamics. I'm going to get through basically latent heat, and I'll save the first law of thermodynamics and thermodynamic processes for next time. But after first law of thermodynamics comes the thermodynamic processes in the first law. So there's a lot of definitions and stuff you need to know there. Molar specific heats for gases and the equipartition of energy. That's another thing that comes in handy. Adiabatic is another term that you'll learn. But it turns out when a process is adiabatic, there's a whole another set of equations you can use, or another equation you can use to help you with it. And we're going to use that ultimately in chapter 20 to help us understand to help you understand the Carnot engine. Okay, so that's one of the fundamental ideas behind the second law of thermodynamics. So that's why we have to cover that. And like I said, we'll do that next time. After adiabatic expansion of a gas, there's heat transfer through conduction, convection, and radiation. So there's a few equations we use on that, and that's basically it. So your book does say, let me see if I can remember if that was James Prescott Jewell, because it was kind of funny. I always mention this to my students, but this is the first time I'd ever noticed that Giancoli had mentioned it too. It's no, that's not it. Ah, British thermal units. This one was before that. I don't see it now. Ah, there it is, Catholic. Yes, so it says the idea that heat is related to energy transfer was pursued by a number of scientists in the 1800s, particularly by an English brewer, James Prescott Joule, who lived from 1818 to 1889. So the James Prescott Joule, he said he's a brewer, and in fact, what I was pointing out, and I normally point out to people, is there's a beer, and it's probably all over Great Britain, but I want to say it was mostly in Wales, but I could be wrong on that. But anyways, there's a beer called Jowls, Joules, and that's from his family. So they were making their money by brewing beer as well as they were making cannons and stuff like that, and for the government and all sorts of good stuff. So in the process of solving such problems, you come up with the founding of science, and that's where we got where we were. So initially what was thought was that heat was a actual fluid. They called it caloric, and we of course use the unit of a calorie based on that, in fact, but we've since discarded that. We know it's not a fluid, but it does in some sense behave as if a fluid is transferring back and forth. But what we've discovered is there's a distinct difference between temperature and heat and internal energy. And that's largely what the book is trying to make sure you understand here. So, temperature, as we learned in the previous chapters, especially the last one, is a measure of the random kinetic energy of the atoms or molecules of uh, of a substance, basically. So if you have a collection, whether it be in a gaseous state, for instance, if you calculated the average kinetic energy of those, you could just multiply it by a couple of numbers, and out would pop the temperature in Kelvin. And that's what we did when we found that E is equal to 3 halves kT. Specifically, kinetic energy is equal to 3 halves kT. I want to remind you that that is for a monatomic gas, and it specifically the temperature part is associated with what we call translational motion, not the ability to rotate, for instance, is a rotational motion, not translational motion. So that's something to keep in mind. Heat, we now see, is a energy in motion. So heat is sort of the energy from a hot body flowing into a colder body, and that is the direction it goes. What we've discovered is that heat spontaneously flows from a warm temperature object to a cold temperature object whenever they're in thermal contact. If they're touching each other, then they can use conduction, which notice duction sounds a little bit like touch, so that hopefully will help you remember. So conduction actually allows heat to flow from one object to another because they're touching. And it's always going to flow from the hotter object to the colder object, the one with the highest average random kinetic energy of translational motion is going to be transferred to the one with the lower average translational kinetic energy. Okay. If you added up all the total energy of all the atoms and molecules in a substance, that would be called the internal energy of that substance or of that sample. So that includes not only the translational kinetic energy, which we account for temperature by, but also the rotational, as well as you could say, for instance, the chemical potential energy that comes from the bonds, or the nuclear potential energy that comes from the nucleus. All those different types of energy all combined make up the total internal energy of an object. Most books use U. Your book is using E with a subscript int internal. So that's the difference between internal energy and heat and temperature. Hopefully that sticks with you pretty well. But as I told you, initially they thought that heat was a liquid, and they thought it was entirely different. In other words, we've been studying, or we will have studied. Actually, I guess everybody has. I can't imagine there wasn't anybody that got here without taking the equivalent of 241. And in 241, we learned about potential energy and kinetic energy and work and that sort of stuff. Well, prior to James Prescott Joule finding the mechanical equivalent of heat, we thought of mechanical energies like potential energy and work and that kind of stuff, kinetic energy. We thought of that as one thing. And then we thought of heat as something entirely different. In fact, they use different sets of units. We use, of course, the joules now for mechanical energy, but we use the calorie for thermal energy. What James Prescott Joule did was a little bit bigger than you might have thought, because if you took chemistry, you probably just remembered that 4.186 joules is 1 calorie, or 4.186 kilojoules is 1 kilocalorie. Uh, and that's right. That was the result from James Prescott Joule, but it was much bigger than that, because in reality, the joule was associated with mechanical energy, and the calorie was thought to be completely unrelated as being a thermal energy. So we'll start off with that. I'm going to go ahead and share my screen with you guys. So here's the share screen. All right, I'm going to write this definition of the calorie down. The amount of heat required to change the temperature of 1 gram of water from 14.5 degrees Celsius to 15.5 degrees Celsius. Oh, no. Sorry about that. And the calorie, which we say a bunch of different ways. You can say kcal, but you can also say 1 capital CAL, is the same thing except 1 kilogram. So dot 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 dot, so on and so forth. So the kilocalorie is essentially the same thing as we said above. Whoa, no, I don't know how I got there. I think I must have hit the wrong. That's not it. That's not it. Well, this is super helpful. Okay, kill this back. There we go. Okay, so that's the difference in those two. Now, what experiment James Prescott Joule did was this. Basically, he took sort of a container of water, if you will. You can imagine a container of water, and you can imagine it being like that. And what you do is take and put a little propeller in there, if you will. And you can imagine a little propeller being like this. And what would actually go on here is you would have a spool of string tied around it. You would have some kind of mechanism that would be like bearings to hold it in place so it wouldn't fall. The spring or the string would go over a pulley, and then you hang a mass M on that, and that mass would fall a distance H. So if that's the case, you'd actually put a thermometer in the vat of water and see what the temperature changed. And when he did that, what he found was mgh is equal to m times c times delta t, where delta t is a change in water temperature. And from that, he got 4.186 joules equals 1 calorie, or 4.186 kilojoules is equal to 1 kilocalorie, which is also called 1 capital calorie. So the capital calorie is the calorie that we use for eating. So if you look, for instance, on a box of Twinkies or something like that, it'll have calories, and it's that kilocalorie actually. So actually, by doing this experiment, he could tell barely what temperature change happened from doing that, and it was a very small one, but he was got it good enough to do it. And then ultimately, that didn't become just a conversion between units as we treat it. It's actually a fundamental change in physics where all of a sudden they understood that heat, which is something that flows from a hot object to a cold object, was the same type of thing as mechanical energy. So it's a really, really big deal. So let's try an example. How high must a person hike? Whoa. Evidently, I'm starting the word hike with a K today. How high must a person hike to burn 500 calories? A, assuming the body is 100% efficient. And B, assuming the body is only 20% efficient. So what we're looking at is 500 calories. So here's our solution. 500 calories equals 500 times 10 to the third lowercase calories, and then times, we'd say 1 calorie is equal to 4.186 joules. So we're going to say 500,000 times 4.186 gives me 2.09 times 10 to the 6 joules. Now, what we want to do for part A is we want to set that 2.09 times 10 to the 6 joules equal to mgh. Now, what I'm going to assume is it's a big person like myself, so I'm going to assume the person's mass is 100. That's kind of big. That's roughly 220 pounds or so. So that might not be very reasonable for most of y'all. But anyways, we can still do it. So what we're going to find is H is actually equal to 2.09 times 10 to the 6 joules divided by 100 kilograms times 9.80 meters per second every second. And when I do that division, I get 2,135, 2,136 actually, meters. So that's pretty high, right? And you know, if you think about that as feet, what I do if I wanted to convert that to feet is I'd first basically say that's going to be times 3 feet. So I'd say shooting on 36 times 3 because a foot is roughly, or excuse me, a meter is roughly 3 feet. We know it's actually not 36 inches. It's more like 39 and some change inches. It's 39.37 if I remember correctly. But that gives you 6,408 feet. So 6,408 feet already, but I've got that extra 3 inches on each of those. So every four of 2,136, I get another foot. So if I divide 2,136 by 4, if I divide it by 2, I get 1,050, 65, 1,065, 1,069, somewhere around there. And then cut that in half again. I get 1,000, be like 530, somewhere around there. So I can add another 530 to that, and that gets me closer to feet. So you can see it's a pretty big climb. But in part B, if we're only 20% efficient, then we really only have to go about 20% of that distance. So I'll say 0.20 times 2,136 meters should do me. That's going to give me about 427 meters. So that's a typical scenario problem. You can work out some of the details. Just remember, efficiency is what you get divided by what you pay for. So if you're a little rusty on that kind of thing and using percentages, you might want to revisit that. That's just supposed to be basic, you know, boring math that we supposedly all knew from middle school, but I get it. Not all of us are are fresh out of middle school, so it might not be that easy. But anyways, just get your fractions and your percentages and decimals and all that stuff up to par. Anybody have any questions on that example? Okay. So that's a big paradigm shift. It told us something. It told us, you know, hey, this thing that we think of as heat, which spontaneously flows from a hot object to a cold object, is actually just another form of energy. So, in some sense, you can imagine that if I shoot a bullet, say, into a tree, which, you know, sometimes people do that, uh, the entire kinetic energy of that bullet, which is 1/2 mv squared, went to essentially nothing. Like if the tree was shot with the bullet and the bullet got lodged inside of it, then it went from all that kinetic energy to zero kinetic energy. And you'd ask, where did all that energy go? Well, that energy went into not only breaking up the individual fibers of the tree to burrow a hole into it, and not only stretching those fibers and kicking fibers out and making sound waves and all that stuff, but it also went to heating up the tree. So if you actually were to immediately pull out the bullet, you'd find one, the bullet was hot, and two, you'd find that the tree around that area is hot. And that's basically what we're saying is, yeah, guess what? Mechanical energy can at least be partly turned into heat. The big deal is that heat is not one way we put it in terms of everyday life is we say heat is not a very high quality form of energy. And the reason we say that is because once you take a certain amount of energy and convert it to heat, you're never going to get all that energy back out. So in that sense, it's just not as valuable a type of energy as not. You can think about it this way: just take your hand and put it on your desk and just rub back and forth, back and forth, back and forth. You can feel your hand getting warmer, warmer, warmer. You can feel the table getting warmer, warmer, warmer. And what's going on there is you're taking ATP, adenosine triphosphate, the molecule of the energy of life, if you will, to basically make the muscles do what they got to do to push the hand back and forth, back and forth, back and forth. That's turning into frictional heat. And then that heat is heating up not only the desk, but it's also heating up your hand. And if you were to try to get all that heat back, you can imagine like trying to survey individual atoms and molecules in the desk as well as in my hand to try to get exactly the same amount of energy that each one of those atoms or molecules got and pull it back out. It's a low probability event. So that's a good way of thinking about it. And that's a way that's completely consistent with the second law of thermodynamics, which is really, a fundamental law of nature. And it's something we've never found a contradiction in. So we've got that. Now, what I wanted to say next is I wanted to let's see. Oh yeah. So what I wanted to say next was I want to get you into the idea of understanding what internal energy is. So E internal, some books use U is the internal energy. Now you can think of that as the internal energy of a sample. It's the internal energy of an object. It's the internal energy of the substance, all that good stuff. It's the internal energy of an object. And basically you could imagine all of the kinetic energy of the atoms, molecules, electrons, electrical potential energy, nuclear potential energy, chemical potential energy. So if you just add up all the type of energies that all the little atoms and molecules making up an object has, then that sum of all those energies, and it could be quite exhaustive trying to figure it out, is the total internal energy. We indicate that by using the symbol E with a subscript int. Uh, Heat, like I said, is basically the flow of energy from a hot body to a cold body. So think about it this way. Remember, we've learned from the atomic theory of matter, basically, or the molecular theory of matter, whatever you want. We've learned that the kinetic energy is really a measure of the temperature. So if you imagine the kinetic energy of the individual molecules, uh, the average kinetic energy is related to basically the temperature through 3/2 kT. So that alone tells you what temperature is. But now imagine you take two objects of different temperatures. Uh, one could be a piece of iron and the other one could be a piece of aluminum. One of them is going to be hotter than the other, and you put them in contact with each other so that conduction can take place. When that happens, what you see is, let's say the iron's a little hotter. So the iron molecules have a higher kinetic energy than the aluminum molecules. That's not unlike, you can sort of think of it if it's a market difference, both in mass as well as in velocity, then you can sort of think of it as like a Mack truck uh, in a neighborhood driving through and just ramming all the other cars off the road. That's what's happening. You're having these high kinetic energy molecules bombard these low kinetic energy molecules at the interface of the two. So every time one of the low kinetic energy molecules of aluminum or whatever hits one of those high kinetic energy, that molecule of aluminum or atom of aluminum will speed up, and it does so in a non-random way. But eventually what happens is then that collision begets another collision, till ultimately all the individual atoms or molecules all have a slightly higher kinetic energy. That means they've all now, since it's now randomly distributed, all of them have a slightly higher kinetic energy. Therefore, the temperature of the aluminum has increased. If that temperature is now exactly as high as the temperature of the iron, then heat will stop flowing. But if it's not, then it's going to continue to bang against each other until they do reach equilibrium, which is when the two have the same temperature. So that's what heat is, and that's the way that they flow from one thing to the other. Now, what we need to understand is how do we go about getting the internal energy? Well, if you want the internal energy of n moles of an ideal monatomic gas, so let's do this. E, whoa, Nelly. An ideal monatomic. So if you wanted internal energy of an ideal monatomic gas made of n moles, then E internal is just equal to n times, and I say n moles, which corresponds to n particles. Remember, n would just be lowercase n times Avogadro's number. That's just n times 1/2 mv squared bar. But that's also, of course, equal to 3/2 n times k times t. And that, of course, is also equal to, so I'm going to write this again, E internal is equal to 3/2 nkt, but it's also equal to E internal is equal to 3/2. In this case, we'll use the lowercase n times r times t. So that's what it is. Now, you got to remember, I did say monatomic. So that means each molecule has exactly one atom. And by doing that, that means the atom uh, can only have translational kinetic energy. The little energy required to make the atom rotate on its internal axis is nothing. On a axis perpendicular to that's nothing, and then a third axis perpendicular to that's nothing as well. So it's really not an appreciable amount of energy whatsoever in terms of the atom itself rotating. Uh, but that's the only way it can move. So it's just that. Now, if you go to a diatomic one, then you have sort of like dumbbells, like there's a molecule and a molecule, or an atom making up a molecule. And you have the ability to rotate about that axis, but you also have the ability to rotate about this axis. You also have the ability to rotate along it, but that one again is just like the molecule before. It doesn't take anything to make an individual atom or molecule rotate on its own internal axis. So you have to do a little bit more if you're talking about something other than a monatomic gas, but hopefully that gives you a little idea where we're going with that. So that's the internal energy of an ideal monatomic gas. And that brings us now to specific heat, which is where we start to be able to use heat in calculations. So specific heat, whoa, no. Now, the word specific normally means per unit mass. Sometimes it means per unit mole or something like that. So the specific volume, for instance, is volume divided by mass. So it's like 1 over the density. So just to keep that in mind, that's a typical scenario that you deal with when you're dealing with something like specific heat. So what we have figured out is that a certain amount of heat Q, and Q's are symbol for heat. Okay. If you put in a certain amount of heat Q into an object of mass M, whose specific heat is lowercase c, and it should be lowercase because it's uppercase is reserved for the ones that aren't specific. In other words, that would just be like calories per Celsius instead of calories per gram Celsius or something like that. And then times delta T. So when you actually apply heat to an object of mass M, it will change its temperature by an amount delta T given by this equation right here. Okay. And then your book has table 19.1. So means this is a table that you expect to not necessarily memorize, but you need to have it available to you when you're doing your homeworks or doing practice tests or doing tests and stuff like that. Normally, I try to pick questions where they already include the quantities. Uh, I don't, that's not good pedagogy. It's best that a student has to actually look for the quantity that they want. But either way, just make sure you have that available to you and get used to using it. And ideally, you want to really know when it's worthwhile. So, just to give you some ideas, for instance, the specific heat of aluminum is 900, and this one's in joules per kilogram Celsius degree. Notice they put the degree after the Celsius again, but it's also equal to 0.22. And in this case, it's calories per gram Celsius degree, which is also equal to 0.22 kilocalories per kilogram Celsius degree. So that's aluminum. We can look up some more. Ethyl alcohol, for instance, is a big one. Let's go to steel, though. So I'll say iron or steel. That's going to be 450. Or if you go to the calories, it's 0.11. Again, using the same units as the part above. So I'll just say ding, 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 like that. Wood. Well, mercury's kind of neat too. I'll say mercury. So specific heat of mercury. Crazy about a mercury. That's a different thing. So specific heat of mercury, for instance, is 140 and 0.033 in the other unit. Here's the big thing, and this is what makes water so wonderful and also makes, for instance, Great Britain have a fairly decent climate, even though all of Great Britain is essentially at the same latitude as Canada, for instance. Yet the temperature is not like Canada, and that's because they're an island surrounded by water. In terms of liquid water, it's 4,186 joules per kilogram per Celsius degree, or check this out, it's 1.00, and that's in calories per gram Celsius degree. And this is liquid water, by the way. It's got a different value if you use ice, for instance, or steam. Just as an idea, I'll show you, for instance, ice wouldn't be 4,186. It would be 2,100 at -5 degrees Celsius. And that also equals 0.50 at these units. Okay. Steam is 3,470. No, 2010 is steam. So you can see basically what they are. But that allows us to actually use numbers and calculations to do things. And when you look up a table like this particular table is all for 1 atmosphere at 20 degrees Celsius. So all these are 1 ATM and 20 degrees Celsius. In general, of course, the ice is something different, but if you're doing a real project where you really need to know the quantities, then you need to look up the most appropriate values of specific heat. So if you're taking something, say from 3 degrees Celsius all the way up to 100 degrees Celsius, you might have to use 3 or 4 different versions of specific heat from getting from one to the other, but not necessarily. Like I said earlier, water doesn't change by more than 1% all the way from 0 to 100. Merchant, go ahead.
Hey, sorry, can you hear me?
Yes.
Okay, can you read what the bracket on the left side in red says? I didn't catch that.
It's 1 atmosphere and 20 degrees Celsius.
Okay, thank you.
No problem. All right, so that's how this is going to happen. You can see if you're using this equation Q equals MC delta T, if you're using that to figure out how much heat it's going to take to raise a certain mass of water, a certain change in temperature, what you see is the larger C is, the larger that Q is going to be, because Q and C are on opposite sides of the equal, but same side of the fraction bar. So they're thumbs up, thumbs up. So high specific heat means it takes a lot of energy to change its temperature. The fact that water has such a high specific heat tells you that water is a great insulator. And that's exactly, like I said, the reason that Great Britain has pretty moderate climates. Namely, they got a butt ton of water all around them, and it doesn't matter that they're at the same altitude, or excuse me, latitude as Canada, because they have so much water surrounding them. It's fine. Whereas if you go to the same latitude in Canada, where it's let's say like in the Yukon territory or somewhere where there's a lot less bodies of water and it's just open land, you'll find that's frigging freezing. Whereas even if you go to the middle of Great Britain, it's not big enough to be that far away from the water. So. Anybody have any questions on that? All right, so let's look at an example. Let's say how much heat is required to raise the temp of iron from, and let's assume it doesn't change too much over the entire range of the temperature. Let's say from 0 degrees Celsius to 100 degrees Celsius. And B, how much energy to raise the same amount of water. Notice I didn't yet give you the actual measurement of the thing of the iron. I'm going to say 30.0 kilograms. So we're considering 30 kilograms of iron and 30 kilograms of water. In part A, we want to know how much heat is going to be required to raise that from 0 to 100. And then part B, we want to know the same thing for water. So this is a pretty straightforward, quick calculation for part A. We're going to say Q for iron is equal to 30.0 kilograms. Now, if I look back here, I think I recorded iron. Yes, I'm going to use the 450 joules per kilogram Celsius degree for the specific heat. And I'm going to say delta T is 100.0 minus 0.0. And of course, that's Celsius degrees there. So we can do that. We're going to get 30 times 450 times 100 gives me 1.35 times 10 to the 6 joules. Notice the kilograms canceled out with the kilograms, the Celsius degree canceled out with Celsius degree, and that gave me that. Now let's try part B. QH2O is going to be, in this case, it was 4,186 joules per kilogram Celsius degree times 30.0 kilograms. Notice I'm running roughshod over the order that I put the equation in. Times 100.0 minus 0.0. Again, that's Celsius degrees. And in this case, I get 4186 times 30 times 100. And we get 1.26 times 10 to the 7th joules. So you literally need a whole order of magnitude larger, quite a bit larger, in other words. Anybody have any questions on that one? All right, so that's really what you have to be able to do this. And there's a lot of different types of problems. For instance, it has a conceptual example. You accidentally make a bad mistake by letting an empty iron frying pan get very hot on the stove, 200 degrees Celsius or even more. What happens when you dunk it into a few inches of cool water in the bottom of the sink? Will the final temperature be midway between the initial temperatures of the water in the pan? Will the water start boiling? Assume the mass of the water is roughly the same as the mass of the frying pan. Anybody want to take a poke at that? I've got the chats turned on again, so in case y'all try to type something to me instead of saying it. I'll read it again because y'all weren't necessarily ready. So you accidentally make a bad mistake by letting an empty iron frying pan get very hot on the stove, 200 degrees Celsius or even more. What happens when you dunk it into a few inches of cool water in the bottom of the sink? Will the final temperature be midway between the initial temperatures of the water in the pan? Will the water start boiling? Assume the mass of the water is roughly the same as the mass of the frying pan. Anybody have any ideas on that? How about that more specific question? Will the final temperature be midway between the initial temperatures of the water in the pan? So let's say the pan was 200 degrees Celsius and the water was, I don't know, 10 degrees Celsius. Would it come halfway between those two numbers? So 55 degrees Celsius.
Or shouldn't the water boiling?
You broke up a little bit. You want to try that again?
Wouldn't the water be boiling because it takes more energy to raise the temperature of the iron rather than the water?
Gotcha. You're not been given enough information, so that's a very common mistake. The fact that the specific heat of water is so much higher than iron, like I said, it's 450 versus 4,186, means that the final temperature is going to be much closer to the temperature of the water. So instead of 55 degrees Celsius, it'd be more likely to be 12 or 20 degrees Celsius at most. And I would really be surprised if it got over 15. It won't boil because this is the part you haven't been given, but there's another equation, Q equals MC delta T. There's another equation like that for when something changes state. So when you go from a liquid to a gas, which is what boiling is basically, there's an extra amount of energy that has to be kicked in. So that actually makes it even less likely. Now, in principle, the hotness of a single part of the iron pan can hit a small amount of water and that would boil away. That's called the Leidenfrost effect. You've probably sprinkled water on a hot frying pan before and seen it skedaddle across the pan. In fact, that's a test of what you're supposed to use to see if your pan's ready to cook a steak, for instance. So that does happen, but that's when the mass of the iron greatly, greatly, greatly exceeds the mass of the water. In this case, where they're about the same, there's no boiling that can occur. Y'all get that? Any questions on that? So that was example 17.3, or excuse me, 19.3. Now, we go into calorimetry, and what I'll tell you is that calorimetry is basically based on a system where you assume that the net heat in the system stays in the system. It's not going to be lost to the atmosphere. And the way we do that in practice is we'll actually have a container like this that's made out of aluminum. And then that aluminum container will have sort of a step side to it like that. And then this side will do the same thing again. And it'll come down to here. And by having that step side, it gives you a little ledge to set stuff on, which is good because what we're going to do is we're going to take an actual wafer of an insulative material like cardboard or something like that, or maybe even just plain particle board like that. And that gives you a nice little ledge to set stuff on in general. Okay. So now you can take a small container, which would maybe be like this, but has a little lip out like that. And now that little edge right there and there can lay right on top of that wafer. And because of that, the only way heat can be transferred from the outside aluminum container to the inside aluminum, they're both aluminum, by the way. And this part, like I said, is cardboard or wood. The only conduction that can happen is through this little itty bitty edge right here that's actually touching the inner cup. Chase, stop it. So it's that little bit that's touching it, and there's an air gap everywhere else. So if I actually drew the cup in place, you'd see the cup like this, and there's an air gap in there. So that also being capped off prevents, sorry about the dogs. So that prevents conduction and convection. So normally what would happen with convection is the hot object inside could heat up the air being heated would be less dense, it would float up, and then that would heat something else up. But that cooler air that fell back down would go back down and get warmed up again. So by doing all that, we basically say that this, Chase, shut up. This comes close to an adiabatic process. And that means Q is equal to 0. And what I mean by that is heat from the air does not get in and heat from inside the container does not get out. It even has a lid on it, and there's a hole in the top for you to stick your thermometer through and another hole for you to stick a stirrer through if you want, all that kind of stuff. All of that is a calorimeter. It's a particular type of calorimeter. Okay, so we want to try to solve a calorimetry type problem. So let's do that. Let's say if 250 cc's of tea at 98.0 degrees Celsius is poured into a 165.0 gram glass cup. Actually, let me see if I got any better values than glass. I'm going to look and see if I can find that for something like a ceramic or something. Let's see. We have marble, lead, glass, copper. It looks like we only had glass, so I have to use glass. 165 gram glass cup. And that cup is at a temperature of 20.0 degrees Celsius. What will be the final temperature? So I want to know what the final temperature is. The way I do this, and different books do different ways. A lot of books just do Q equals 0. And what they mean by that is the sum of all the positive and negative Q's add up to give you 0. But that requires you to remember what we consider a positive Q and what we consider a negative Q. What I've discovered over time from being a student and being a teacher is that students can sort of get which things are losing heat and which things are gaining heat. So I use something else. What I use is this. I say Q gained equals Q lost. So I take everything that's losing heat and put it on the right-hand side, and everything that's gaining heat, and I put it on the left-hand side. So if you think about this, we have 250 cc's of water. I should mention that the density of water is equal to 1 gram per cc. So that basically means that this is 250.0 grams of water. So what's gaining heat? Well, we're taking this really, really hot water at 98 degrees Celsius and we're pouring it into a glass. So clearly the thing gaining the heat is the glass. So what I'm going to do is I'm going to say the mass of the glass, and I actually probably should stick it to black. I'm going to say the mass of the glass times the specific heat of the glass times the delta T of the glass is equal to, now that's the only thing that's gaining heat in this problem because we actually have a glass that we're pouring hot water into. Now, the only thing that's losing heat in this case is the hot water. So I'm going to say the mass of the water times the specific heat of water times the delta T of water. Now, in generally, delta means final minus initial. However, when I make up this system, it's not that way. So, however, in using Q gained equals Q lost, I have to make each term positive. Okay, so that's the advantage. So if something's getting warmer, then final temperature minus initial temperature gives you a positive value. So you just use final minus initial. But if something's getting colder, like the water is, then you use initial temperature minus final temperature. So it comes out positive. So now let's go ahead and write this up and see what we can get. So I'm gonna go back, and the mass of my glass is it's a 250 cc cup of tea. Excuse me, the mass of the water is 250 grams. The mass of the glass is 165 grams. So I'm going to write 165.0 grams. Now, what we know is the specific heat of of glass. I'm going to go back and look at that table. Specific heat of glass is 0.20 calories per gram. So that's 0.20 calories per gram Celsius degree. And then remember, the glass is actually going to be warming up. It's going to go from, like 20 degrees Celsius to something higher. So we're going to do the higher thing, which is the final temperature, T final, minus 20.0 degrees Celsius. So that's how I made it positive. Now on the other side, we've got the mass of the water, which is 250.0 grams times 1 calorie per gram Celsius degree times, now this one, the water is actually going down. So I want to have the initial temperature first. So I'm going to have the initial temperature, which is 98.0 degrees Celsius minus T final, like that. So that forces this to be greater than 0, and that forces this to be greater than 0. Okay. So I can take my 165 times 0.2, and that gives me 33. So I'm going to say 33. Sorry, I switched to blue again. I'm going to say it's 33.0. That's one extra sig fig. And that gives me calories. The grams canceled out, C Celsius times T final. So that's what that one is. Now, if I take that 33, I also have to multiply it by negative 20. That's going to give me negative 660. So minus 660. That again is only good to 2 sig figs, but that one we actually managed to multiply everything out. So that's just calories. Then the other side, we're going to have 250 times 1 times 98. That's going to give me 2.45 times 10 to the 4th. And that one is actually calories minus 250.0 times TF. Okay. And of course, that one has units of calories per Celsius degree. So I can get all the TFs on one side. 33 plus 250 would be 283.0 TF. That takes care of this term and this term. And then over on the other side, I'm going to take that 2.45 times 10 to the 4th and add to it 660. And that gives me 2.516 times 10 to the 4th calories. And then finally, that gives us T final is equal to 2.516 times 10 to the 4th calories per 283. Now I'm going to put those units back in, which are calories per Celsius degree. So we're ultimately just going to get Celsius degrees, which we can automatically just assume it's going to be degrees Celsius. So I take that 25160 divided by 283, and that gives me 88.9 degrees Celsius. So you can see the water changed very little temperature-wise, and that's because the water is such a has such a high specific heat. Any questions on that one? So that's the way I tend to do my calorimetry problems. I just, like I said, I take all the things that are losing heat and I put them all on one side and I make sure all the terms are positive. Then I take all the things that are gaining heat, I put them on the other side and I make sure all the terms are positive as well. And then I just solve for the variable that I want and that gets it for me. So anybody have any questions on that, how that worked out? You can try the delta Q equals 0 case as well if you'd like. And you might actually should just to see which one you like. Try using delta Q equals 0. Maybe you will prefer it. But to be honest with you, it's not quite fair doing that until this next part. And the next part is what comes after just changing the temperature. So for instance, you know that changing the temperature requires a specific heat adjustment. But guess what? It also takes a certain amount of heat to break bonds. So for instance, if you have something in the solid state, you have all these atoms or molecules that are in a lattice. So it's like a atom or molecule here, then some equilibrium distance between it and the next atom or molecule, and then some equilibrium distance between it and the next, and so on and so forth. And then forward, there's another equilibrium distance between it and another molecule and another molecule, and then backwards and then below and all that stuff. So you get this sort of three-dimensional array of atoms and molecules. That's an actual force that's holding them in those places. So if you want to not only bring the temperature up by Q equals MC delta T, you're also going to have to add some heat to break the bonds between the individual molecules. And that is called latent heat. So let's start off with latent heat. So latent heat is normally given the symbol L. And what we say is Q is just equal to M times L. And there's L sub F, which is the latent heat of fusion. So if you imagine the heat of fusion really is the heat of something going from a, let's say, a solid or liquid state to a solid state. Then there's a heat of vaporization, LV, and that's the latent heat of vaporization. So that's in going from a liquid to a gas. And this one's from a solid, or actually from a liquid to a solid. Now, this is the part where I was telling you stuff gets a little hairy, because you got to remember, hey, if I go from a gaseous state to a liquid state, does that require me to put heat in, or does that give me heat out? Because that matters, right? It's going to be negative in one case and positive in the other, unless you do it my way, where I just say Q loss equals Q gained. Same thing with going from a liquid state to a solid state. Does that give off heat, or does that take in heat? Well, I happen to remember that one of the things that happens usually around fall, we have the strawberry farms around here where people can go pick strawberries and stuff like that. And you often hear weathermen say, oh, we're going to have a chance of frost tonight. And you'll hear that the strawberry farmers decided to go water their strawberries. Well, what they're doing is they're watering their strawberries. So the strawberries are out in the field. That night, they expect it to get so cold that water is going to freeze. So what they do is they spray the strawberries, they get a coat of water on them. Then the temperature gets so cold that the water on the outside freezes. But when the water on the outside freezes, that actually is an exothermic process. That's a process in which you're taking a lot of extra energy it had, because all the atoms and molecules were separate, not rigidly tied into a molecular structure or into a atomic structures like a lattice or anything. And it gives off that extra energy that it had from all those things being free. And in so doing, it actually gives a little boost of heat to the strawberry that helps it not freeze. Not only that, as you saw, the specific heat of water and even ice is still pretty good. So you now have little clear coats on the strawberries that are insulating them, as well as a little boost of energy they got. Does that make sense? You also have, let's see if you guys can guess this one. L sub S. Anybody want to guess what kind of heat that is?
The heat of sublimation.
Exactly. Latent heat of sublimation. And that's when it goes completely from solid to gas. Okay. And just like we had a table for that, we have a table for this. In fact, you can just take individual water molecules and think of them this way. So let's say this is a plot of temperature versus heat added. So this is going to be the amount of heat I added, and this is going to be the temperature in degrees Celsius. And I'm going to start way down here at -40. And then I'm going to say this is -20. And then I'm going to say this is 0. And then I'm going to go from 0 to 20, 40, 60, 80, and then 100. And then maybe 120. That's plenty enough there. So what we're going to have is for the first 20 kilocalories, so this is heat in kilocalories, we're basically going from water at -40 to water at 0, like that. So you can imagine that slope means something, or maybe it's 1 over the slope that means something, but you should think about that a little bit. And inside of here, we know that we have ice. And then what we have from 20 to the next 100, which I'll say is 40, 60, 80, 100. So I'm going to put the 100 right here. I have from there to there, I have to put in 100 calories. Now, this is all 1 kilogram of H2O is what we're dealing with here. And then once I get to that 100 kilocalorie mark, I'm still at 0 degrees Celsius, but all of a sudden I'm going to jump all the way up to 100. And I'm going to say this is 200. And I'm going to say 3 more is 300. And that should be pretty good there. So now I'm going to take this line and go from here to here. And then, no, I don't want that one. 400 is right here. And then 500 is right here. 600, 700, and 740. Now I got a little bit off linear there, but that's okay. The 740 is where this is supposed to end up at. So I'm going to here. I'm going to keep this all at a constant temperature all the way to there. And then it's going to fly upward from there. So this is all water and ice. This one's all water. And this one's all water and steam. So you can see how you can't just put in calories according to MC delta T. That's what gives you the slope lines. But there's also an amount of energy where the temperature doesn't change. And going, for instance, from 200 kilocalories to 740, the temperature didn't change at all, but you still had to add that much heat. So you can imagine, evidently, the latent heat of vaporization here should be 540. Does that make sense? So that's LV there. And then, of course, you can see that the latent heat of fusion and going from about 20 to 120, that, or to 100, excuse me, that is actually 79.7 kilocalories. So hopefully you can now sort of see how this is going to be taken into account. So now we don't only have Q equals MC delta T, we also have Q equals M times one of the L's. And this is the L fusion. Your book defines the heat required to change 1 kilogram of substance from solid to liquid is, oops, I said it backwards. So I'll write a mark through that. From the solid to the liquid state is called the heat of fusion. It is denoted by L sub F, and that one's right. And the heat of vaporization is the heat required to change a substance from liquid to water vapor, from the liquid to the vapor phase. So liquid to vapor, yes. So that one's right. Any questions on that? All right, well, I think that's good enough. We only got like 4 minutes left. But you can see table 19.2. Now remember, just like, last semester, they're going to assume you have this stuff. So this is another table. You either need to keep like a picture of it on your phone, or a picture of it on, or a drawing of it or something like that, because you will need it when you're doing homework, when you're doing practice tests, and when you're doing tests. Again, with the practice test and the test, they almost always have it built into the question, but also I tend to have it as a separate thing from the front cover of your book or whatever. So you guys are free to go. I'm waiting around for the last person to leave in case anybody have any questions.
I have a question about this chart. Are we going to be supplied with that on a test, or do we need to make a copy of it? If we have it on a test. No, it'll be okay. Okay.
Yeah,
All right.
yeah, it'll be included either through the test or in the questions for it. But when you're doing homeworks, yeah, you got to have it with you.
Okay. All right. Thank you. That's a
No
good
problem.
question. All right. And this was good for tomorrow also, right?
Yes.
Yeah. Okay. All right. I got to go take care of my dad now. All
Yeah,
right.
sorry about that, Sean. Have a good one, hon.
Okay. Bye. Bye. It's okay. It's okay. I'm fine. All right.
You have a good day, Mr. Younger.
You too. Thank you.
This
Uh,
is
per-
what you said for the table, yes? It will be provided during a test?
Yes, I will definitely give you those values during the test. I'm just saying during homework, you need to expect to have you look it up.
The graph as well?
Not so much the graph. Actually, I've always used this graph to memorize the values for water myself, just because I knew it. But you don't have to have that graph at all.
Okay.
Professor,
Yes.
I think you were talking about like different heat capacities of different materials.
Mhm.
So that would that be provided in certain questions, or is that like the table that you're talking about will be given?
I would prefer to test you by giving you tables, but
Okay.
generally this author has put them all in the questions, so it's a little easier because they'll literally give you exactly the figure they need. But they do, to make up for it, on occasion they'll give you a figure that you don't need. So just be careful of that. Make sure you grab the right one.
Okay. All right then. Thank you.
You're welcome.
All right. Bye bye.
Have a good day, Mr. Younger.
You too. Thanks, Elijah.
Professor, I have one question. I hope somebody didn't already ask you this.
That's okay.
The question about the mastering physics assignment at the beginning of class.
Right.
I didn't know what she was talking about. All I'm tracking on is really like the labs and then the 2 homeworks that happen in
So
my lab math.
they're not mentioned like in Canvas, but when you go to My Lab and Mastering, you'll see among the assignments there's one called Intro to Mastering, and then there's another one called Physics Primer. But honestly, I count those as extra credit. They are due tonight. If you do them, or if you're not that familiar with My Lab and Mastering, then I would recommend you doing them. If you do them late, it's not going to matter. I'll still give you full credit, but really you should do them. But if you've already done something like it and used Mastering Physics, don't even bother. It's just extra credit.
Professor, I was looking at it. It said the 29th, not the 22nd.
Did it? Okay, that makes more sense. I
That's
thought
why I
I
was
put
confused. I
another
was like,
week back.
Oh, yeah, no, I see it too. Yeah, that makes more sense to me.
Because I was flipping
Yeah.
out. Why is there something I didn't do? I usually
Yeah,
try to
I
get
just
it.
I think a student might have said something, and I assume that's what they said, and it might not have been what they said at all. So it could have been me just mishearing. But yeah, if it doesn't say that, then it's definitely not this week.
Also,
Yeah, next week. Yeah.
Professor, I've noticed, between the inertia of getting the class started, I guess, the old lab links that we were doing in lab were on the for the homework were in the class, but I noticed you put them in the lab.
Right.
So I've double.
I
I
haven't
saw
done
them that
anything in there yet, though.
yeah, I saw that you put them in the lab module, and at least the assignment 1 and 2. So I just attached the stuff I put in the class module in there, and then I just said, "Hey, I put this also into the class module."
Okay.
Does that make sense? Like,
Yeah,
it'll
yeah.
show late. One of them will show late on the in the lab module, but it's in the class module. Am I making myself clear?
Yeah, yeah, I get you. It's not going to be a problem. In fact, what normally happens if I find the majority of them are in the other class, I'll just get the whole class to put it into the other one, and I'll give them a couple days to do that or something. So just watch out for me asking you to move it to the other one. I haven't even done anything with your lab one yet. I'm just trying to figure out what students are in lab with us that aren't our online class, that aren't our face-to-face class. Once I get that, then I can start doing stuff with that lab one. So don't worry, I'll give
All
you
right.
plenty of time. I'm not going to take off points. Worst comes to worst, I'll grade it over there and transfer the grade to the lab one. Does that make sense, Jerry? I might have lost you.
Yeah, it did.
Okay, gotcha. Anybody else have anything?
Nope. Thank you, Professor.
Thank you. And like I said, I'll let you know by 5 tomorrow if something happens and I can't do Wednesday, but I'm pretty sure I'll be there. I'm getting sick of being here. I don't want to be here anymore.
Tracking. Thanks.
All right. See you, Martian. Ariel, do you have a question? All right. Looks like everybody's gone. So bye-bye, everyone.